Before I get started, I want to do an exercise to put us in the right mindset. So I'm going to draw this interval here. 0.1 to 0.2. And it's a half open interval. So a half open interval is one in which you have, so this is saying every real number between 0.1, including 0.1, up to but not including 0.2. So if we use a round bracket for the end of an interval, we are saying that that endpoint is not included. So for example, this is a fully open interval, 0 to 1. Every number between 0 and 1, but not including 0, not including 1. And this interval, 0 to 1 in square brackets, is every number between 0 and 1, including both endpoints. But over here we have a half open interval. Everything between 0.1 and 0.2, not including 0.2. And the first bit that I want to, the little exercise to put us in the right mindset, is I would like to assign, inside of this interval, not including 0.2, I would like 20 different fractional values that lie in this interval such that the number of decimal places used is as small as possible. So I want to use as few digits as possible. It's a compression task. I want to use as few digits as possible, but I need there to be 20 distinct things. So here's what I would try doing. I would say, okay, I need 20 things. 0.1, 0.15, or no, whoops, sorry. 0.10, 0.105, I was off by 1, 0.11, 0.115, all the way down to 0.190, 0.195. And you can satisfy yourself that there are, in fact, 20 things there. And I had to use as few digits as possible. If I wanted to use, if I could cram them all between 0.100 and 0.105, but I want to use as few digits as possible. And these used at most 3 digits. Okay, so the second version of the same exercise is do the same thing, but do it between, let's pick some other values. How about we pick 0.5 up to but not including 0.7. Notice that this half-open interval is larger. The width of this interval is 0.1. This one is 0.2. This is a larger interval. Here's what I would do there. 0.50, 0.51, 0.52, all the way down to 0.68, 0.69. And there are 20 of those. Notice that I was able to come up with this, and I used 2 digits. Just to make it clear, I was able to solve the problem with fewer digits. Notice that because I had more real estate to work with, it was easier for me to use fewer digits. And in fact, it was possible for me to use fewer digits. You might be able to observe there is no way of doing it inside of this interval that uses 2 digits. I have to use 3 for at least one encoding. The reason I want to bring this up is to observe that, okay, there actually is no shortage of, space between 0.1 and 0.2. We know that there's an infinite number of real numbers between 0.1 and 0.2. If I'm quantifying a real number's complexity by the number of digits used, then there is some advantage to having a larger interval to work with, at least in base 10. Turns out it's the case in base 2 as well. The bigger the interval is, the shorter I need to encode a specific number of things that fits into that interval. And it actually turns out we can generalize that as the number of things that we take the limit as it goes up. Basically, if I find that I'm going to need the things more often, then having the things encoded into a larger interval, an interval that is wider, might result in them having fewer digits. We'll see why that comes up in a few minutes. We're at that point in the course, and maybe it has something to do with this word. We're at that point in the course where we need to do one more thing before we can polish off lossless encoding. And then we can all take a break until some point in early July. And we've talked about Huffman coding. We know that Huffman coding is a form of entropy coding. And it's one of these things that can reduce a sequence, if we assume all of the characters are independent, down to something pretty close to its entropy, bounded below only by this issue that Huffman coding has of needing a whole number of bits per symbol. There is one other big method for entropy coding that doesn't even need to do it that way. It's able to use less than 1 bit per symbol in some cases, and a strange sort of fractional number of bits, and it's arithmetic coding. We're going to talk about that, and these half-open intervals will come up later. What I want to observe for now is that although when we talk about real numbers, a lot of our usual assumptions make very little sense, which is to say there are an infinite number of values in a range, the size of intervals can have an impact if we choose a finite encoding. So here's a Huffman code. And we see we've got some text fragment, we have a Huffman code I've generated for it, and we've noticed that we have entropy, which is the average number of bits per symbol based on their information content, and we've got L bar, which is the weighted average number of bits per symbol based on the length of their encoding. And it's off by a bit. We know that we can't do any better than entropy, so we're off by a bit, and we know that any error therefore has to make the L bar value larger than entropy. But Huffman coding does a pretty good job. It turns out that we've already seen that even the most basic prefix code we came up with in the prefix code lecture was off from entropy by at most 1 bit. But Huffman coding can actually do much better than that. If the largest probability of any symbol is this value p max, then we actually can define a bound on the error between the L bar produced by Huffman coding and the entropy in terms of p max. In particular, note that if you have a huge number of symbols and they occur with a distribution that's relatively flat, then you're going to have a pretty low p max, and you'll probably fall into this case down here. It turns out that Huffman coding can actually give you entropy. You can't do better than it, but you can't do better than entropy in general. Huffman coding can actually give you an encoding that exactly matches entropy if you're lucky enough to have this situation occur. So if the information content of every symbol is an integer, Huffman coding can give you an encoding for each symbol whose length exactly matches information content. And that means you get L bar equals entropy guaranteed. The only time you're going to get information content being an integer is if the probability of each symbol is a negative power of 2. And that's because information is computed with a log in base 2, and so those would cancel out. Now that's great, but obviously that's not going to happen very often. And we can take, if we want to see the other end of that, we can take those bounds or fiddle with them and observe that there are ways of getting Huffman coding to be very wrong. We know that it can't be off from entropy by more than 1 bit, but we'll see in a minute we can actually drive that error all the way up to 1 bit. It doesn't have to be, we saw it was like 0.03 or something a minute ago, but it could be higher than that. So one way to do that would be to observe Huffman coding can't give us an encoding any shorter than 1 bit, but we can make the information content of a symbol less than 1. And we can do that by making that symbol's probability be incredibly high. And so here, one thing interesting to observe is the information content of every other symbol is 5.8. And all of the encodings are actually shorter than that. So it's doing pretty well on everything else. It just can't overcome the deficit it's in because it's losing 0.87 bits for every A that gets encoded. And maybe we shouldn't think about this too much. Like maybe this is a sort of a conjured up example. You should know better than to necessarily think poorly of an algorithm because of an example somebody put in slides. But if we were to get neurotic about it, think about if I'm encoding 1 million A characters, then 870,000 of those bits have gone to waste. There's only actually 130,000 bits of information in 1 million A characters. And so I'm wasting a lot of bits there. And so in this case, on average, I'm actually using twice as many bits as necessary to encode, or just about twice as many to encode a symbol. We can make the problem even worse by observing that all we have to do is have one symbol have a vast majority of occurrences compared to the other one. So if I made a string of the form n copies of A followed by B, and then I take the limit as n gets larger and larger, I can drive the information content of A asymptotically towards 0. And yet, Huffman coding can't do any better than an L bar of 1 because it needs to use 1 bit. And so I can actually make entropy get lower and lower and L bar stay at 1. And so I can actually bring the error pretty much all the way up to 1 asymptotically. which isn't very, that's not fair. This is definitely a bit of a gotcha example. We don't usually expect to see this situation. An alphabet of size 2, where one symbol is extremely common, we would not throw Huffman coding at that as our first technique. We would try something else, run length encoding probably. And so we can think about this difference here between this and this, so about 0.6 in this case, as the average overhead per symbol. The amount of overhead Huffman coding imposes per symbol as a result of what it does. And the overhead is caused by this need to use a whole number of bits for every symbol, because it encodes each symbol in a vacuum, effectively. It just encodes each symbol by itself and then concatenates all of the bit encodings of each thing. And so 0.6 bits is not a big deal. But the issue is this is per symbol. If I encode 1,000,000 symbols, I lose 0.6 bits per symbol over entropy. And again, it's no big deal if I can never achieve entropy, but it's something to think about. It's one reason to begin searching for something different from Huffman coding to encode long sequences. And of course, we do encode sequences with billions or trillions of symbols. And so we do want the ability to reduce that overhead as the sequences get large. So we're back to the age-old question. Okay, so the first thing, just a disclaimer here. Huffman coding, if you encode one symbol, if I give you a probability distribution on a set of symbols, I don't care how many symbols there are, 1 billion symbols, who cares? If you get a probability distribution for any set of symbols, and you do Huffman coding, and you encode one symbol, and you send me that encoding, the encoding you produce will be the shortest possible. Period. That is not a deficit of Huffman coding. Huffman coding is perfect when you are encoding one symbol. You cannot do better for encoding one symbol than Huffman coding. The problem is we aren't encoding one symbol. We are developing a code for single symbols and then employing it repeatedly. There's always going to be a little bit of error. I can't send you 3.7 bits. If I'm sending you one symbol and I have to round 3.7 up to 4, that makes sense. Huffman coding's error is no better than anybody else, or is no worse or better than anybody else's error. So that's the first thing we have to get behind us. Huffman coding is perfect for one symbol. We just don't use it that way. Now, on the other hand, what I could think of is, wait a minute, if you hand me the probability distribution of every individual symbol, so A is 0.3, B is 0.2, I could try and reduce this overhead. If I'm transmitting 1,000,000 characters, then I have to round up 1,000,000 times. I'm transmitting 1,000,000 different symbols, and Huffman coding for each symbol has to round up to a whole number of bits. What I could do is think, maybe if I came up with a way of encoding this 1,000,000 character sequence into fewer symbols. So one thing I could do is I could say, why not combine together A and B into one symbol? And there's some stuff we have to think about there. So first, if we assume every symbol is independent, then we can use this identity from probability theory, which you probably have seen in some point in the past, probably in 226, which is if two events are independent, the probability of one occurring after the other is just the product of the probabilities of both of them. So the probability of seeing a message AB, those two characters in a row, is just the probability of A times the probability of B. And this is the identity that I'm using. So for example, if you tell me you're going to send me a 2-character message, then instead of just creating a Huffman code on my single characters and then sending me 2 symbols worth of encoding, you could just work out the probability of every 2-character message directly using this identity. And then you could develop a Huffman code on that here, and you could just send me one of these things. And if it were only a 2-character message and you sent me just one of these encodings, it would be optimal. You couldn't do better than that. This error here is the result of having to use a whole number of bits, which is fine. And if you think about it, you could do that for any length of message. And I want to go back to this slide that I skipped over to point this out. So what this is assuming is that you gave me a probability table, just this, and you told me all characters were independent. If they're independent, then the probability of A followed by an A is just this times itself, which is 0.49. And the probability of A followed by a B is 0.7 times 0.2, which is 0.14. If you actually had not that you would ever do this, but if you had an actual input sequence, as you often do when you generate Huffman codes, you would probably just go through it and work out the actual frequency of AA. because you know that your input sequence would not be perfectly independent. We're talking about Huffman coding conceptually here, and we'll see, because the point I'm building to basically is something Huffman coding can't do practically. So if I encode my entire message, suppose it was a 2-character message, if I encode my entire message in one symbol by making a Huffman code over every possible 2-character message, and I send you one symbol, it's guaranteed to be perfect, the best possible encoding. I could do that for a 3-character message as well. All I have to do is work out for every 3-character message. So I could say, well, what's the probability of the message BCA? Well, it's 0.2 times 0.1 times 0.7. And I could work that out for every 3-character message. I could take the resulting probability table of the 27 possible 3-character messages. I could build a Huffman code, and then I could send you the Huffman coding of one of those messages. And that would be perfect. There'd be no better way to encode a 3-character message. And the overhead that we get is overhead that we have to put up with no matter how we do it, because we can never send a fractional number of bits. This is great. I can do this for 4-character messages. I can do it for 10-character messages. The problem is, how do I build a Huffman tree over all possible 1,000-character messages? I mean, how do I enumerate them? If I have 256 possible symbols, as I often do, then the number of 1,000-character messages, the number of possible ones, is this. And just so that we have some perspective, that's 2 to the 8,000. That's how many entries would be in my table if I could generate that table. I don't even think I could list everything in that table in the amount of time left before the death of the universe, much less store everything and run Huffman coding on it. Although actually, incidentally, n log n in this context is only 8,000 times 2 to the 8,000, so the log n term still wouldn't hurt us too much. One reason why n log n is actually pretty close to linear time. So I can't do that. If I was able to send a single symbol, then Huffman coding would be able to do the trick. Every time, I could never get a better code length than Huffman coding. The problem is, I simply cannot work out the probability table for the size of input that I'm working with. So what I have to do is I have to decide, okay, my symbols are 3 characters each, or 5 characters each, or 1 character each. Make a Huffman code for that, encode each character separately or each symbol separately, round up for each symbol, and then incur whatever error exists, whatever difference there is between entropy and L bar, which could be as much as 1 bit for every symbol. So I can't do that. And so for some reason, I'm going to give up. I'm recording this on a Sunday night. So maybe now it's time to just start with a completely irrelevant aside. So I'm, as you'd expect for somebody such as myself, I spend my leisure time, like my Sunday night, on my various erudite leisure activities, thinking about the big questions. And so, of course, what I'm going to think about today is, can we treat an entire data stream, so you begin sending me bits. Can we treat an entire data stream as a single number? And you'd say, well, that's not a big question, Bill. Of course we can do that. I mean, come on, give me a break. It's been 2 months of this. We can do that because if you send me these 4 bytes, I'll just say, sure, I'll just call that huge 4-byte sequence one 32-bit number. And it happens to be this number. Okay, great. So what's so exciting about this? Well, my issue with this is this doesn't really match what I mean by a stream of bits, does it? I mean, if I tell you I'm going to send you 4 bytes, and then you wait until all 4 bytes arrive, sure, you can frame them, and you can put them in a box, and you can say this is a single 32-bit number, and you can tell me it's this one. But is that how compressed data streams actually work? I think instead, you send me bits, and I begin receiving them. And I don't want to have to wait until I've received the entire bit stream to draw conclusions about this number. So suppose the number is, we'll call it x. It's this, and we'll just say it's this in base 2. Suppose I've received 4 bits. Can I say literally anything about x? Can I ask the question, is x in the range, I don't know, so 1011 would be the number 11, I guess. So is it in the range 11 to 1100? Do we know? Nope. We have no idea. Not until you send me more bits. In fact, you don't know anything about x until you've seen the last bit. So if I want to treat my entire stream as a number, I first off have to store the entire stream, which I don't want to do. I have to wait until I have the entire stream before I know literally anything about x. Besides, I suppose there are a few obvious things I know, which is at this point, if I have at least 4 bits, and they are prefixed by the encoding for 11, x is greater than 11, but I don't know what it's less than. And I can't make any other conclusions about it until I've seen all of the bits. And I also can't compare it to any other bit stream I might know about until I've seen all the bits. For example, if you begin sending me this bit stream here, y, can I ask the question, is x less than y? And the answer is still, I don't know. It's certainly, I've constructed a y where it looks a bit suspicious. It looks a lot like y is less than x. In fact, I could even do something really sneaky like this. But it turns out I can't answer any of those questions. We don't know how many more bits are in z, or x, or y, or anything else. We know nothing about any of these numbers. And so if we treat them like an unsigned integer, we have to wait until we get all the bits, and then we can compare them. That's not the answer to the big question I like to think about in my erudite leisure time. So what I want is the ability to work with the number from left to right. I don't want to wait until I have the least significant bit to know something about a number. And so I begin thinking, here are some numbers I work with in my everyday life. 1, 2, 3, 4. And if you send me the digits of 1, 2, 3, 4 in base 10, I don't know what number I'm working with until I get the last digit. And it's reasonable. I may not know everything about the number until I get the last digit. I want to know something. So I think, are there any other numbers you could send me, digit by digit, where I would know something about it before you sent me the next digit? And I think, what if you sent me this number? I'll call that x. X equals 0.123 something. I don't know what it is. At this time, immediately, so I'm treating the number as a decimal expansion. You're sending me digits. I'm treating every digit as the next digit in a decimal expansion. I already know that x is somewhere in the range 0.123 to, let's see, 0.124. Not inclusive. So 0.124 is not going to be the value of x. The more digits you send me, the more I can refine my estimate. If you begin sending me a number y, I already know that x is less than y. Anything more you tell me about x might give me more information, but I'm actually able to work with these digit sequences from left to right, because that's how we work with the expansion of a real number. And really, it's because the center of the universe is our decimal point, if you think about it. Things expand outwards from there. So there's the answer to the big question. But I'm not asking about things in base 10. I'm asking about things in binary. So can I treat a binary sequence as a fractional value starting from the decimal point or something similar to that and working my way to the right? So you send me the bits 1, 0, 1. And there's some more to come after that. Well, I think what I could do, I'll call it b. b equals the following value, 0.101 in base 2. And just to remind you, the way we compute the decimal value of a fractional value in base 2 is just like we would for unsigned integers. We start by taking our bit sequence and we take a look at this thing, which is not really called a decimal point because it's not a decimal number. We call it a radix point for lack of anything better to say. Some people say the binary point. I don't know about the binary point. So we'll say the radix point. And we write underneath every value a negative power of 2. And then we erase all the powers of 2 underneath zeros. Whoops, and we accidentally erase the entire page because we forget our hotkeys. So here's my bit sequence again. And so b equals, this is a good opportunity to do it properly, to write it out more neatly. b equals 101 in base 2, 0.101. So we write our negative power of 2 under each digit. And we erase the power of 2. We press the right hotkey this time. We erase the power of 2 underneath every digit that's a 0. And we add together what's left. So this is 1/2, and this is 1/8. And I'm going to cheat over here, and I'm going to just figure that out over here. So it's going to be 0.625. plus something. I mean, there could be more in this expansion. And in fact, the way base 10 works, it could even affect some of these digits. But the idea is, if I have a fractional value in base 2, it has all the same properties as a fractional value in base 10. It's just, as with any other change of base, all I'm doing is modifying the representation. So I can treat a bit stream that you send me, bit by bit, as a fractional value that's unfolding before my eyes. I know that fractional values have an infinite expansion, and so it can keep going as long as I want, but I can start learning about it as I get each bit. And this is pointing out an earlier disadvantage that I mentioned, which is that not only do we not know much about the number, if you treat it as an unsigned int, not only do we not know much about the number, but also in our books, this sequence is different from this sequence. But if these are the beginnings of unsigned int representations, it could be the same, like that is to say, these two things interpreted as binary numbers are equal. I don't want that. These three leading zeros could be really significant to me. And so treating these as fractional values gives me exactly what I want, which is that leading zeros make a lot of sense in fractional values. They're significant. And so I can do that. I can represent a sequence of digits that you send me or a sequence of bits that you send me as a fractional value in whatever base we're using, so binary, in this half-open interval. Because, of course, if I assume that the digits you send me are the ones that come after the radix point, then you're never going to be able to send me the number 1. Every number is between 0 and 1, not inclusive of 1. And so if I take that sequence from earlier and I encode it as this fractional value, and you send it to me bit by bit, by the time I've gotten only these first 2 bits, this is 2 to the negative 2, we'll call this x. Well, actually, this means that x is in the range, okay, so 0.01 in base 2 is 0.25. X is now somewhere in the range 0.25 up to, well, what could it be? Well, I guess x is definitely less than this number. So this bit is a 0, which means x has to be less than 0.1, which equals 0.5. So x is somewhere in the range 0.25 to 0.5. So even with only for the first 2 bits, I already know something about the numerical representation. And moreover, what's really interesting is, and this part is sort of obvious, but what's really interesting is every single string that you could send me that began with the encoding of the letter A would, of course, be in the same range. It would also be somewhere in the range 0.25 to 0.5. Pretty deep in there, because, of course, the letter A has got a lot more bits than what I've demonstrated here. And so there are, of course, similarities. I mean, the encodings are grouped the natural way, and they're now grouped numerically. They now occupy a consecutive we don't want to say sequence, range of real estate inside the real number line. So, okay, what are we doing? What's the deal with this? I thought this was a leisure activity. Well, yeah, so this is a good idea, I think, because we've found a new modeling technique. Even if we never developed, even if we ignore this second paragraph, even if we never develop a clever encoding scheme from this is a clever idea because it can allow us maybe to say things, to prove things or justify things about what we already know, things like Huffman codes maybe, because we can begin talking about stuff in terms of their fractional real number representation. On the other hand, it turns out the reason we're doing this today is because this technique called arithmetic coding, and I think I've changed my mind about this. By the last set of slides in this sequence, you'll see I think I capitalize A and C. It deserves to be a proper noun. It's not named after a person, but it deserves to be a proper noun. We'll see arithmetic coding actually relies on using these real number representations as a way of achieving a more efficient, in terms of overhead, encoding than Huffman coding. That said, we should be careful here. So if we redefine the universe to work in terms of real numbers, the kind of real numbers that can have an infinite number of digits, we have to be careful that we might get in some hot water if we ever want to represent those real numbers with a finite number of bits. So, of course, by changing the setting of our compression technique, we might discover some amazing things. That doesn't necessarily mean that we're out of the woods. We still have to figure out a way of actually representing it using binary values. So let's go back to our Huffman code. And what I've drawn over here on the right is sort of a diagram to sort of segment the possible real estate. Now this is true, what I'm about to say is true for bit sequences of any particular length, but let's think of the bit sequences of length 4. So I'm going to write them all down from top to bottom. And we'll notice that they segment quite neatly. And I mean, I've drawn them this way, but the real estate is divided up between the strings that begin with, here's B, and here's C, and here's A. And we'll notice that I've drawn the diagram deliberately to show this effect, but because of the way that I have encoded A, B, and C, because of what Huffman coding did, you might notice 50% of all sequences begin with A. And 25% begin with B, and 25% begin with C. This is true no matter how many bits I had in my sequence. Sequences of length 4, length 5, length 6, whatever, 50% begin with A. And you'll notice that that's because there are two possible first bits, 0 and 1. Everything beginning with 0 begins with A. So 50% of sequences begin with A in this case. Okay, so we can visualize the Huffman code in terms of the fractional interpretation by starting there and working our way into it. So half of all bit strings begin with A. And actually, maybe I should write that. Let's just think about this in terms of percentages. 50%. And then, that's a pretty ugly way of... It's Sunday night, so I'm not drawing as well as I would on a weekday. Okay, so then this is 25%, and this is also 25%. And one observation I want to make is that I don't think A deserves 50% of the real estate. And I don't think B deserves 25%. I don't think C deserves 25% either. If it were up to me, I would say, if I could choose any number, I would say, well, if I look at an arbitrary sequence, if I choose any sequence of symbols, I should expect that there's a 45% chance A is the first symbol. That's what probabilities mean. And therefore, if it were up to me, A should be only 45% of the real estate, and B should be 35, not 25. So here, A is being overrepresented with its 50%. And B is being underrepresented with its 25%. Why is that a big deal? Well, that's because I have a 35% chance, or 35% of all bit strings symbol strings I could look at begin with B. If all of the encodings of those strings have to be crammed inside of 25% of the space, so I have 35% of my symbol strings being crammed into 25% of the space, I guess I have to make the encoding longer. That example from the very beginning where I showed that if I have to cram 20 things into a small interval, I need more digits than if I cram them into a large interval, that's what this was referring to. So the issue here is that B is not getting enough real estate for its importance, and C is getting too much, and so is A. Both of them are getting 0.5 more than they should. But Huffman coding can't help that. Huffman coding either assigns an encoding of 0 or it assigns an encoding of 1. It doesn't really have the ability to say, okay, A, you get 45% of all sequences. And we'll also notice, of course, this applies recursively, I guess, as you go further through. So among the sequences beginning with A, there are some that begin with AB, there are some that begin with AC. They're precisely the ones that are a 0 followed by, let's say, a 1, 1. And, not that it should surprise you too much, but if 50% of all sequences begin with A, then 25% of all encodings will begin with AA, and we will have 12.5% begin with AB. Down here we have 25% of encodings begin with C, and I maybe leave myself enough space, 6.25% are CC. Now the issue I mentioned before, I think C is overrepresented. C gets 25% of the real estate here, but it only actually deserves 20% of it. And you can actually see that in the information content as well. C gets 2 bits, but actually has 2.3 bits of information. A gets 1 bit, but has 1.15. B gets 1.5 bits of information, but actually gets encoded into 2. So B is underrepresented. And here, the actual probability of seeing two C's in a row, of being in this box here, is 0.2 times 0.2, which is 0.04. Whereas it gets 0.06. It gets 6% of the real estate. So it's again overrepresented. And the error is now sort of getting larger. I mean, as the message gets longer and longer, the error compounds. The overrepresentation or underrepresentation gets worse and worse the more of those characters you see in the message, because Huffman coding has no way of balancing things out. And ultimately, that's the problem. It's that every symbol being encoded separately means that you have no way of reversing the error that begins to pile up as you go along. Now, the reason that I bring this up is that actually we can see what I just described in numerical terms. It jumps right out at us. I don't need to draw all over the diagram to get the same effect, because what I can observe is, okay, wait, sequences beginning in 0 are A, beginning in 1, 0 are B, beginning in 1, 1 are C. So every sequence from 0, 0, 0, 0 to 0, 1, 1, 1, 1, 1, 1, 1, all of those fall into this bucket. They're the A's. Every sequence from 1, 0, 0, 0, 0, 0, 0, 0 up to 1, 0, 1, 1, 1, 1, 1, those are the B's. It sounds a lot, if I use the fractional interpretation, therefore, that every number, if I interpret my encodings as fractions, every number between 0 and, well, this is 0.5, every number between 0 and 0.5 corresponds to a binary encoding that starts with A. Every number between 0.5 and 0.75 is an encoding that begins with B. Every number between 0.75 and 1 is an encoding beginning with C. And so I actually get this table of what I think we can call encoded probabilities. So with Huffman coding, the probability of an encoding beginning with A is 0.5. The true probability of A is not 0.5, but the probability implied by the encoding is 0.5. And so the slides are working backwards to what I just said here. And just an editorial note here. So I could actually represent all of my probability values in base 2, but because it's easier for us to reason about numbers written out like this, I'm going to do that. Keeping in mind, it's just a base change. Nothing like the number itself is always the same in both cases. And so the problem we have with Huffman coding ultimately is just that Huffman coding doesn't have enough granularity. That's it. I mean, we know that, yes, the bits are the problem, but really it manifests itself in this view, which is Huffman coding can't give me 0.45. It can give me an encoded probability of some power of 2, basically. And so it's able to say 0.5 or 0.25 or 0.125, but it can't say 0.45. It just can't do it. And so as a result, we need more granularity if we want to recover this extra 0.5. Because I'd like it if A went from 0 to 0.45 and B went from 0.45 to 0.8. And C went from 0.8 to 1.0. That would give each symbol its true probability as its encoded probability. So the question is, how do we do this? The slides aren't ready to get there yet. And so then there's this question just to reinforce, okay, wait a minute, why is it better for a more frequently occurring symbol to have a bigger interval? Really, I'm presupposing for some reason that A having a big interval, because it's like A should have an interval of length 0.45 and B should have one of 0.35. Well, I've just drawn a diagram. Have I really proven anything? Why does this make a difference? So we don't have much appetite for the proof on this, but basically that example I did at the very beginning is intended to motivate this. We know that there are an infinite number of sequences, of encoded sequences that begin with C, and an infinite number that begin with B, and an infinite number that begin with A. In fact, if you think about just in terms of strings of C's, B's, and A's, there are the same number of strings out there in the world that begin with a C than there are that begin with an A, right? You could just relabel a C as an A. However, it's more likely that I'm going to see a string beginning with A. So what I want is to make it so that it's easier to encode strings beginning with A. There are the same number of strings of a given length beginning with A as there are beginning with C. There are n strings that begin with A and n strings that begin with C. By making it so that I've got this much space to fit all n of those strings, I potentially can use fewer digits or bits or whatever to represent it, as we saw in our example from the beginning. I was able to encode 20 things into a small interval using 3 digits and into a larger interval using 2 digits. Ultimately, that's our motivation. I want the size of the interval to reflect the true probability of the symbol, so it's neither over nor underrepresented, and that I can encode strings beginning with that symbol into an amount of space that is just given that probability. And so this is talking about this is trying to justify that with a different approach. It's pointing out that, again, without a proof, all we can do is talk about this diagram, which I just invented. Like, who's to say what this diagram actually tells us besides what I'm claiming it says? And so there are ways of justifying this much more formally, and but for our sake, we've had a rough time in the last couple of weeks, so we're just going to push on through. So here's what I want. I would like to have some encoding mechanism where I can get close to, keeping in mind some errors might happen, I can get close to my true probability for each symbol. And this is under our usual assumption that all symbols are independent. We'll notice in our third part that we can actually break that assumption once we've gotten the mechanics of this technique down. So the question is, can we actually do this? Can I get it so that every bit sequence between 0 and 0.45 begins with A, decodes to A, sorry. Every bit sequence from 0.45 to 0.8 decodes something beginning with B, and everything else decodes something beginning with C. Can I actually do that? I can get pretty damn close, as it turns out. But I can't achieve it in general. So the obvious example is if I look at messages of length 1, I can't. Seriously. Like, if I'm going to send you one symbol, I have to encode A, B, and C somehow. Well, I'm not going to waste bits trying to encode A in a strange way. I'll just encode A in 1 bit and B in 2 bits, right? I mean, that's the best way of doing it. We know because we've proven Huffman coding does the best on one symbol. So on a small number of symbols, we might not be able to get there because it might take a while. We might need a few symbols to have enough traffic to divide up the possible strings among the buckets so that they work out to 0 to 0.45, 0.45 to 0.8. In this case, there aren't enough the rounding we have to do between bits and probabilities is too harsh here. We need more symbols to make this possible. The technique we're going to describe, which is called arithmetic coding, ultimately does actually achieve entropy on messages as the length becomes arbitrarily long. It approaches entropy over time, as opposed to Huffman coding, which stays equally far apart from entropy the whole time. It doesn't get further away, but the errors keep adding up. And so it's pointing that out, yeah. So we can actually observe that, for example, that the message beginning with BB has a true probability of 0.12, but its encoded probability, because B is underrepresented, so BB is even more underrepresented, is only 0.06. That's half as much. And we can actually observe that the true probability here is 0.12. The information content of 2 B's is 3.03. The information content of 1 B is 1.5. So the problem here is that this is still not, I mean, this would still round up to 4 bits. But think about it. 3 B's might be representable in 5 bits, or might have information content between 4 and 5, whereas 3 B's with Huffman coding would be encoded into 6 bits. Okay, I got ahead of myself here. So if I look at the probabilities for 2-character messages, 2 B's is 3.03 bits, which would be, I guess Huffman coding, even in the best of times, would round that up to 4 bits. Fair enough. 3 B's is this, 4.5 bits. And that means if I did a Huffman code on all my 3-character messages, BBB would be 5 bits. But the problem is the Huffman code on single symbols will generate this, 101010, which is 6 bits. And so I've now lost an entire bit already with 3 symbols in some cases. That's 1 whole bit for 3 symbols. And so, again, let's put our minds in the place where we are encoding millions and millions of symbols at a time. Okay, so one last thing that we have to think about. Suppose that you know somehow, I tell you, I'm going to send you a 2-character message or a 7-character message. Or I encode some information into the message, for example, an end of message symbol or something, such that you know how long the message is. So suppose you know the message is 2 characters long. The messages beginning with AC fall inside this interval, which is this. If you know the message is 2 characters long, and I send you the value 0.38312, you would decode that to AC, and then you'd just be done. You wouldn't care. If you know the message is only 2 characters long, you would figure out that this number is somewhere around there and say, okay, we're in the AC block, so the message must be AC, and we're done with it. Any value in the range 0.375 to 0.5 would be something that decodes to AC. So if you know that you're sending a 2-character message, and you know that whatever you send has to be a number somewhere in this range, what do you send? Okay, well, it depends what base you're using. But if I were sending you a message in base 10, I would send you this one, 0.4. Because I would notice somewhere in this range, which goes from 0.375 to 0.5, and it's not inclusive. 0.5 is not in the range. Somewhere in there, I want to find the shortest encoding I can send you. And it's my choice. Any number in that range is valid, because any number in that range can be decoded to AC, followed by other stuff that you don't care about. So I would choose, it's my choice, I would choose the encoding that has the fewest digits. I would choose 0.4. That's something we're going to put that in our pocket for later. Really, when I'm encoding a message with anything, it's even saying prefix code, but with the technique we're about to describe isn't prefix coding. When I'm encoding a message, what I'm actually doing is I am finding some binary value, a single binary sequence X. That is the encoded sequence Huffman coding produces, somewhere in the range PQ, where PQ is the encoded probability range. So in this this is the table coming out of Huffman coding here. The way it chooses it is sort of complicated. It's not obvious how it does that, but it finds some value inside this range that acts as a representative of that symbol. And remember that if I send you this sequence of encoded bits, which would translate to, I guess, BCAA, when you look at this, remember that the actual binary fraction representation, like any other real number, has an infinite sequence of zeros at the end, right? Like if I tell you, here's a real number, well, this is actually the same number, so is this, and so is this. You can have as many zeros as you want. We know already that's why with Huffman coding we have to use this end of block marker to make it more obvious that, it's time to stop. Otherwise, theoretically, there are just an infinite number of 0 bits waiting to be decoded otherwise. So here's what I want. So here's the past. This is what Huffman coding gives us. It takes our sequence of probabilities, it creates this encoding. The encoding implies this encoded probability. So that's this, and that's this. The encoded probabilities do not necessarily match the true probabilities, and they compound. So 50% of things begin with A, which means of the things that begin with A, 50% are beginning with AA. And that compounds over time. And so we get things like B is underrepresented with 1 character. It's even more underrepresented after 2 characters. All I want is this. I would like to have the encoded probability of each symbol equal its true probability. So the real estate for A sits between 0 and 0.45. And the real estate for AA sits between 0 and 0.45 times 0.45. And the real estate for AB sits between 0.2 and 0.36, which is 35%, the width of which is 35% the width of 0.45. That's it. And I want that to go all the way down. I want that inside of here, this would be broken up into A, B, and C as well. And I want every time it's broken up, I want it to be broken up by this set of probabilities or as close to that as we can possibly get. I'll tolerate a small error, 0.44, 0.36, whatever. I do not want it to be 0.5 and 0.25. So why not just do that? Like literally, why not just do that? I can work out the true probability range of AB. The strings beginning with AB are the values between 0.2 and 0.36. If I want to encode a 2-character message, and it's begins and it's AB, I just figure out something inside this range to send you. I guess I would probably send you 0.2. If my message began with AC, I would say, and I know it's 2 characters long, I would say, wow, okay, the range 0.36 to 0.45. I would probably send you 0.4. All I want is to work out for a given message where it falls in this set of nested ranges. And then I choose a representative inside the block that corresponds to my message. And of course, again, this can go down as many levels as we want. We can keep adding more and more decimal places to make our messages larger and larger. And once I get down to a specific block, like this one, I choose any representative I want, because I know that once you're in the block, you're good. You have the message you want. And we'll see that choosing a representative is actually surprisingly easy once we get to that point. The slides agree with my earlier example about AC. If I want to encode the message ABB, then I would just go down further. So here I have the probability range for A, which is 0 to 0.45. I just expand that, so 0 to 0.45 is now the whole thing. And then I want to encode ABB, which means AB is this range here. ABB is the middle 35% of that, so it's 0.27 to 0.33. I would probably choose 0.3 as my representative because that uses fewer digits. It's my choice, and if I'm using base 10, 0.3 seems like the most convenient choice to make. In base 2, I would do the same thing. So remember, these numbers are all the same in any base. It's just the representation that changes. In base 2, the range 0.27, 0.33 is this sequence of values. So what I would probably choose, observing that I'm going to write the 2 endpoints of the range on top of each other. So here's the low point, 0.0100, 0101, and then the high end of the range is 0.0101, 0100. And I observe I need any number between those two things, not including the high point. So this is not included in my half-open interval. And I would observe that this number, 0.01010000, is sufficient. It's bigger than this thing, and it's smaller than this thing. And if I don't worry about the trailing zeros, I can send it in 4 bits. That's the logic I want to use. If I want to encode BBB, okay, first, here's the range for a single B, 0.45 to 0.8. BB is just the middle 35% of that, and BBB is the middle 35% of that, 0.66 to 0.71. So in base 10, I would probably choose 0.7. In base 2, it turns out I choose this thing. So the low end is 0.1010. The high end is bigger than 0.1011. So I just choose 0.1011, which is apparently 0.6825. Not that that makes too much of a difference because we only care about one base at a time. You'll notice that if I do that, I'm encoding BBB, and I was encoding earlier ABB in 4 bits. If I go back and look at my probability table, BBB's information content is around 4 bits. Now, it's true that if I'm using 4 bits, I'm apparently encoding it in less than its information content. Well, that's just sort of luck. Don't read too much into that. In the same way that Huffman coding occasionally assigns a shorter encoding than the information content, on average, this new technique isn't going to give us better than entropy. Huffman coding gives us 6 bits. So I've saved 2 bits in that encoding. So arithmetic coding, what I just did was a simple example of arithmetic coding. And the difficulty of arithmetic coding isn't the concept. It's still going to be a bit alien to people, but it's not the concept. It is how do we implement it? And there's a whole other lecture about that. That's what I mean by the difficulty. It is a pretty simple algorithm that, given a probability table, or given a way of computing the probability of each symbol at each step, let's put it that way, it computes the true probability range of an entire message. So just to clarify, the probability range of the messages beginning with BBA is this window here, 0.61 to 0.66. Arithmetic coding takes this and gives me back that range. And then I can choose which representative to use from that range. And decoding just basically starts inside the range and works its way out. And so what we do is we begin, like we did back here, we start at the range 0 to 1. And at each step, we refine our window. If my first character is A, then my window changes because I know first I had no characters to begin with. Now I see an A. And I know that A's have to lie in the first 0.45 of my current window. So my window narrows in to be 0 to 0.45. At the next step, I see the character B, and I know that B goes to the middle 35% of my window. So my window narrows in further from to the window 0.2 to 0.36. My third character is also B, so my window narrows further, and then it stops if the message is over. So all arithmetic coding does is that, and it starts at the initial range 0, 1. So when you have 0 characters encoded, the probability window is everything available, 0 to 1. Now we have to define a couple of things. So what we have to do is, you might notice the probability of B back here is 0.35. And yet we never actually see a 0.35 anywhere. I mean, the window for B is 0.35 wide, but we don't see 0.35. That's because B occupies the next 0.35 of real estate after A. And so what we actually want to do is sort of define, okay, so the range for A is 0 to 0.45. B is wherever that left off, 0.45 to 0.8. We're going to call this the cumulative probability. So we just take the probability of all the previous values, and then the window is the sum of all the previous probabilities as the low end of the range, and then that sum plus the probability of the current symbol as the high end of the range. And so I'm going to call it the cumulative probability range, and I define it as a half open interval. So C low and C high of each symbol. And C low is just the sum of all the probabilities of previous symbols. So I have to define some implicit ordering of symbols here. So A, B, C, whatever. I have to define some ordering. Who cares what it is? I just have to make sure I'm using it consistently. The low end of each range is the sum of all the probabilities of the previous symbols. The high end of each range is the low end plus the probability of the current symbol. So the low end of the range for B in the previous example was 0.45, the sum of the probabilities of everything up to and including A. And the high end of the window is 0.45 plus 0.35. So there's the probability for B. And that actually ends up equaling 0.8. Okay, so that's the first bit of notation. You can also define it this way with this recurrence. If you want to write a for loop to compute it, this might be easier to do. You might also know that it turns out that the low-high thing is actually a notational convenience, because the high end of the range for this symbol is just the low end of the range for the next symbol. So you could actually only have to compute the lows, and then you can use that identity to get the highs out of that. And so what I do is I encode my sequence of symbols by narrowing down the probability range using those cumulative probabilities. So I have my range for all symbols, and then I narrow it down depending on which symbol I just saw. If I see an A, I go to that top bit. If I see a B, I go here. If I see a C, I go into this window. Suppose I want to find the range for the sequence BAC. Okay, so B has the range 0.45, 0.8. So I zoom in on that. And then, okay, here I've zoomed in on B, and I notice that B's, I then take this initial thing, and I basically just scale it into the range 0.45 to 0.8. And then I look at the next symbol is A, which is the first 0.45 of my window, which is up to here, so 0.61. And just to be clear on how I'm doing that, the way that I scale my cumulative probabilities, so here are my cumulative probabilities unscaled, 0.0, 0.45, 0.8, 1. The way I scale them is if I'm inside of a specific window of this low and high, I scale the low and high cumulative probability with this equation. This isn't very exciting. This is a typical linear scaling equation, but there it is just in case we want it for completeness. So if my next symbol is A, then I zoom in on this bit here, and I scale my range again. So I scale the entire table to fit inside of this range. And I just keep doing that. Every new symbol I add, I just scale this in, and I keep refining my range. Now, you might think, obviously, we're going to have an issue if my message is 1,000,000 characters long. I'm going to need a huge number of places of decimal precision. Yes, that's going to be a problem. But if we're talking about real numbers in the abstract sense, that's not a problem in this lecture. So that actually produces a pretty simple algorithm. All I'm doing is a bunch of scaling operations and looking things up in tables. So let's run through it. Now, remember that, again, if I'm sending you this arbitrary sequence of digits, I mean, 0.0110110, and I stop sending you bits, what I'm actually sending you is a real number, which means every real number has an infinite sequence of zeros at the end of it, so I could just keep decoding forever. So I have to have, just like Huffman coding, I have to have some way of telling you that the message is over, stop decoding it. Like otherwise those sequences of zeros would all be decoded into A's or something. So we have to add this extra symbol at the end. We create a symbol where if you ever see it while you're decompressing, you just stop immediately. It's not part of the message, it's the end of stream marker. But it is a real symbol, so we have to give it a frequency. It has to have a probability. It has to actually it has to be represented in my probability table. So traditionally, we give it a frequency of 1 and a probability accordingly. And then if you're decoding and you hit that marker, you're done. Stop decoding. Okay, so at each step, our algorithm is going to track the upper and lower bounds of our range, keeping in mind that the high value is not actually in the range. It's the smallest value outside of our range. So at the beginning, before I've encoded anything, those values are set to 0, 1. At each time, so I'm just going to quickly scroll back up. I'm going to need to keep doing this scaling equation, and you'll notice at the bottom, the denominator is the high minus the low, so I'm going to compute that here. At each step, I compute the difference between my high and my low. I look at my next symbol. I figure out its cumulative probability range, so the symbol's A, so it's this. And then I apply the scaling to scale my probability window and to scale my bounds. So my probability of A lay in the range 0 to 0.43, the cumulative probabilities. It should be no surprise that my new window is just 0 to 0.43. So this 0.43 has been rounded, but maybe you get the idea. So I just apply this equation to scale my low-high window according to whatever symbol I just saw. So after I encode A, I get 0 to 0.43. Notice that B, because B's probability range is between 0.4 and 0.7, I should assume that my window will be narrowed to sort of somewhere in the middle of that range by the next step. And sure enough, it is. My window was 0 to 0.4. Now it's 0.18 to 0.3. And I encode the A, and then I end up 0.18 to 0.23. And I just keep doing this. I just keep narrowing my range. And we'll notice that as I narrow my range, one thing to hold on to for the next lecture is, as I narrow my range, we get to this step here, the range is now 0.210 something up to 0.211 something. And the range only ever narrows. It's never going to move. And it turns out that once there are shared digits at the beginning of both low and high, they're always going to be there. So low and high will always be prefixed by 0.21 from now on. Now I finish encoding. I've encoded the end of block marker, and my final range was 0.21154 to 0.21167. I have to choose any number I want in that range and send it over to be decompressed. So I'll choose something that works well. It's my choice. If I'm working in base 10, I would probably choose 0.2116. That's 4 digits. If I'm working in base 2, I've highlighted which bits are in common. Here are the common bits between the two numbers. In base 2, I need some number that is greater than or equal to this and less than or equal to this. So I could always just send you the low value, but if I do that, I have to send you 5 extra bits. I could also choose a value that is somewhere between the two of them. And so in this case, what I observe is that this is 0, 0. So if I choose this but 0, 1, it's still less than this, but it's also greater than this. And so I could choose that as a 13-bit representative. I could save 3 bits. And it turns out, not that we care, but it turns out that's equal to 0.211547, just to convince you that it is in this range, even if I convert back to base 10. So here's my encoding procedure, assuming that I've got some magical computer that can have an infinite level of precision in real numbers, which I do not, but this is it. This is all I have to do to encode. The difficulty is figuring out a way of implementing this. Okay, so here I have a really skewed frequency distribution. Remember that Huffman coding really had a hard time with this, where A would be encoded, so A's probability is 0.7. Huffman coding would encode A into 1 bit, even though A contains fewer than 1 bit of information. So we'll try encoding this. I go through the entire encoding process. I end up with a 20-bit representative that I send across. So I've encoded it in 20 bits. In Huffman coding, if I include an end of stream marker, which I really should do, it takes 26 bits. Even if I don't, though, it takes 24. So I have now saved bits. Now, but who cares? People put examples in slides all the time. And remember that the reason it would take 24 bits is just because all 14 occurrences of A need 1 bit apiece, even though A only contains 0.5 bits of information. Here's the even more skewed example we saw earlier, or one of them. I think it's a little bit less skewed than the one of those we saw earlier. A's probability is 0.84. We run through this. It's a long message. If we run through this, we get 45 bits. So there are 50 characters. The input has 50 characters in it. So just to be absolutely clear about what we've done here, I've taken a 50-character input, even though it contained a bunch of symbols whose probability is low and information content is high, and I have encoded my 50-character input into 45 bits. So I've definitely beat Huffman coding. I don't have to look at what Huffman coding does. Huffman coding can't give me any better than 1 bit per symbol, and I've beaten it already. If I use Huffman coding, just because I might as well to rub it in, Huffman coding, the actual information content of all of these other symbols is pretty big. 5 bits, 3 bits, 4 bits, 5 bits. Huffman coding would require 64 bits to encode exactly the same message as this. Because, of course, it needs more than 1 bit per symbol, or at least 1 bit per symbol. The issue here is arithmetic coding is able to get closer to actually, because it can give A the fair amount of real estate it deserves. A deserves 85% of the real estate. Because it can do that, arithmetic coding can get an advantage. It can encode A's into clearly fewer than 1 bit per symbol. And it turns out asymptotically, the number of bits that A gets encoded into asymptotically approach 0.25 bits. So this can break the barrier that causes all that overhead in Huffman coding. And then we're not done. This is still enjoying my victory lap here. So here's an even more extreme distribution. Actually, okay, so we need to, the word extreme this is not necessarily a more extreme distribution. I think maybe I'm going to change that wording. Extreme implies something different, but this is a distribution that breaks Huffman coding. Because we'll see that it has more of an error in Huffman coding than the previous one did. So this, we can use 44 bits. 25 characters, 44 bits, so just under 2 bits per character. If we go look at what Huffman coding's doing here, so what I'm actually pointing out is that there's an error. The error term is bigger, and that Huffman coding doesn't do a very good job of getting any symbols information right. So it's either underestimating or overestimating the number of bits per symbol. And it takes 44 bits with arithmetic coding. Huffman coding doesn't do too badly because it can do 48 bits, because it is saving some bits. Like this is 1.4 bits of information, but it gets encoded into 2. And this is 4 bits of information, but gets encoded into 3. So Huffman does save some bits just as much as it loses some. So really, the reason arithmetic coding is so helpful is that the message isn't constrained to a whole number of bits per symbol. The message ends up being one number. That's it. There is no requirement that we round up to a number of bits, except at the very end when I choose my representative. And so there is no artificial obstacle that constrains it in terms of how each symbol is encoded. So it can get closer to the true information content of each symbol. That said, we've just gone on a long victory lap celebrating how much better the encodings are. Let's be very careful here. So, arithmetic coding, in my opinion, is a very good example. So arithmetic coding does work really well in practice, just to be clear. We'll see that. We haven't seen it yet. A lot of algorithms, though, don't have that property. They sound great on paper, and you really can sell them well in a lecture. You can make great-looking slides, fancy-looking diagrams. I obviously haven't done any of that here, but you can make an amazing textbook chapter about how great this algorithm is and how fast it is, and then nobody's ever been able to implement it. That's happened with a lot of algorithms over time. And we talked about some earlier in this course where they are implementable, but they don't actually have the benefits they appear to have when you write them. Arithmetic coding does, but we don't know that yet, so don't necessarily fall for this. It's what I would call a textbook algorithm until we've demonstrated that it's practical. So what is so difficult about implementing it? And the problem is we need to represent real numbers. And here, oh great, I was using, 16 digits, but that's fine. But if I'm encoding a million things, I can't fit all those digits in a double. And unlike ints, I can't chain together double values. Floating point arithmetic is not as easy to work with as ints. And I don't have the ability to work with double precision floating point values that have a million bits in them. And not only that, this spoiler here points that out. Some people are sitting there thinking, but yeah, can't you use big decimal in Java? There are libraries that let you do arbitrary precision arithmetic. There are, but if you want to do arithmetic on floating point values with millions of bits of precision, you're going to be waiting a long time for each multiplication to finish. You will not have a practical algorithm. So we have to overcome that problem. Not only do we need a lot of bits and a lot of digits in our number, we would really rather avoid having to do arithmetic on all of the digits. If you think about it, when you multiply two real numbers, you may need every digit of all of those numbers. And that means if you have a billion digits per number, you're not going to be able to compute things in any reasonable amount of time when you have to do one or multiple multiplications per symbol that you encode. So let's think about these things for later. First, how do I actually decompress this in streaming order? So if you don't send me the entire number, you just send me a sequence of digits, how do I get each symbol? How do I pull each symbol out without actually having to see all of the bits that you've sent me yet? And then how do I choose a good representative? This is actually going to be really easy when we get to it, but we haven't gotten to it yet. How do we choose a good representative besides eyeballing it? When we decompress, what do I need? So for Huffman coding, it does magical things too, but we've learned by now you have to give me the Huffman tree or the Huffman codes or the code links or whatever before I can do the decoding. And as I'm sure you've all learned from assignment 2, actually encoding the Huffman tree is no walk in the park. So arithmetic coding also has metadata. What is it and how do I send it across? Even though that pseudocode looked too good to be true, because it obviously was, where was that? This looks way too simple. Oh, actually, there's also a typo. This should say the input S should be input data there. That pseudocode looks simple. What's actually going on? What is the actual computational cost? And what the issue that this comes down to is if my real numbers are arbitrary precision, I'm going to have to spend a horrendous amount of time multiplying them together. I need to get around that somehow. Let's talk about decompression, though. We can at least demonstrate decompression at the end of this lecture. So, as a topical choice, I want to decode this value with the table of probabilities we were already working with. Notice that even before we started work, even if I only look at the first couple of digits, I actually can see that V lies in this interval, which means I actually know that the first character is an A. And it turns out this is our key for later for how we can decompress in streaming order. I don't need every digit to work out what the next character is. And I actually don't need, I can be, if I'm clever, I've got a lot of ways of having to put off some operations until later. So what I do is I basically duplicate the encoding process. There's a lot of similarities here to the logic behind LZW, where the decompressor just does what the compressor does to follow along, to keep all the same numbers, and just tries to stay one step, stay within lockstep of the compressor. So the decompressor also maintains a low and high window, but it also keeps track of its encoded value, the value you've sent that you want decompressed. And at each step, it takes that value V and it figures out where it lies in the probability window. So it scales V to it scales the probability table to lie between low and high and then figures out where V lies within that window. Here it's obvious because the window is just 0 to 1. So V is the character A. And you'll notice at all times the window low-high, because V, when it was during compression, V was chosen as a representative from the final value of low and high from that window. Low and high as we go will slowly converge towards V. V will always be between those two values. So if I want to determine the next symbol, what I do is I scale the range low-high to 0, 1, and I scale V proportionally using this formula. So it's sort of the same. This is very similar to the formula that I would use to scale the probability window of a specific symbol. So I scale the value of V. I then take a look at that and I compare it to the values of this table, and I discover that this is lying inside the range for A. So that means the next character was A. Then, now that I know that the next character was A, I compress A. I run A through the compression process, and I change the low and high values based on that symbol. Just like with LZW, once you figure out what the next symbol is, you run through the compression logic so that you, the decompressor, have all the same data the compressor does at the beginning of the next step. So I run the encoding logic, and then I queue up for the next step. At the next step, here's my low and here's my high. I scale V to be in the range. I scale the whole window to be in the range 0 to 1. I scale V proportionately. It's 0.47, which means it lies in here. My next character is B, so I run the encoding logic again, and I get this window. And you'll notice it's the same window I had earlier when I encoded AB. And I just keep going. And eventually, if I walk through this long enough, I will hit the end of stream marker. And then I'm done. And as soon as I hit that, I stop. I could keep decoding forever. We'll notice that low and high still have some distance between them, and so I could just keep going forever. If I do, I'm going to get irrelevant data because I know that my message is over. And so there is the pseudocode for the decompression process. Again, it's a bit too good to be true because there's also this ominous looking line. This is this is at worst linear search, but it's certainly, there's something happening there beyond one line worth of work. Our difficulty is going to be, how do we actually write code that does this, given that we don't have infinite precision real numbers with constant time multiplication and addition? So just to be clear, we might, if we're working in base 2 and I use a double, I get 53 significant bits. So the typical format of a double precision floating point value on a computer is 64 bits, but 11 of those bits are used for other things. So we only get 53 significant bits. If I use a long double or something, I might get more. I might get 100 significant bits. Ultimately, though, I need trillions of bits, and I don't have that. And even if I did, how am I going to multiply together 2 trillion-bit numbers, right? So, yes, it's true, there are these arbitrary precision floating point libraries, but they basically amount to making an array of bits or something, or a linked list, or whatever. And maybe you can get variable precision, maybe you can get fixed precision, but it still is prohibitively expensive to do arithmetic. Now, I could maybe pivot and observe that I'm not using transcendental values or anything. I'm actually only ever working with multiplication and division and addition, which means I could represent everything as rational numbers. The problem is I would still need arbitrary precision arithmetic because the numerator and denominator would both potentially become very large. And so I would still be working with rational numbers consisting of arbitrarily large integer values, and that of course would take a horrendous amount of time to perform basic operations. So no matter what option I use, even if I had real numbers of whatever precision I want, I just can't practically do that. So I not only have a speed problem, I not only have a space problem of if I'm storing a real number to represent my range, then I encode 20 gigabytes of data. I guess I have to store that entire real number in memory at all times. I can't even put it on disk because I need the whole thing. I need all the digits to do all my arithmetic. I don't have enough memory for that. Even if I did, how am I going to multiply together 2 20 gigabyte numbers? So those are two problems, and floating arbitrary precision arithmetic or rational numbers do not solve both of those problems. In fact, they don't solve either of those problems, really. So what we apparently need is the ability to somehow magically achieve infinite precision in finite bits. So I need to be able to do all of this stuff in a small number of bits that is bounded above. So no matter how much data I compress, I am not going to have to use more bits because that's prohibitively expensive. So infinite precision in finite bits. Now, that's obviously a tall order, so I'm not going to try covering that now. I will, however, cover how we address this problem for arithmetic encoding in the next lecture, when I'll talk about how to do it in as few as, 32 bits, 16 bits, whatever's convenient for you.